Hello, this is Sergio Cicero from University of Cantabria in Spain, and I'd like to present here this work entitled On the Use of the Combined Fictitious Material Concept and Average Stress Energy Density Criterion for Fractal Prediction of Notched Specimens with Nonlinear Behavior. I am the first author of this work, but I have collaborated with Ali Reza Torabi and Hamid Majidi from Iran and Francisco Javier Gomez from Spain as well. These are the contents of the presentation. First of all, an introduction to set up the scene of this research. Then I will present the material and the methods followed during the research. The third section is gathers the results and the corresponding discussion, and finally some brief conclusions. In this work, we work with short glass fiber reinforced polyamide 6, which is a common engineering material. It is used, for example, in automotive industry, in railway industry, in structural parts, in components with some structural responsibility. The thing with this material is that it is quite sensitive to the moisture level. Small amounts of moisture may change quite a lot its mechanical properties. And this comes together with the fact that the material has high absorption capacity of the moisture. On the other side, the structural components on which this material is used may have notches, which at the end are stress risers, which may cause in the short term or in the long term may cause structural failures. And we all know that when dealing with notches, we need specific methodologies to analyze this kind of effects, because it is straightforward that they are not cracks, as we will see in the next slide. There are different approaches to deal with notches, and one of the most extended ones is the average strain energy density criterion, which is a linear elastic material whose use in elastic plastic situations requires modifications, and a couple of these modifications are the equivalent material concept and the fictitious material concept proposed by Torabi and co-workers. The equivalent material concept works quite well in materials that do not have a linear elastic tensile curve, but have linear elastic fractal curves. The material analyzed in this work has non-linear curves in both tensile and fractal situations, and that's why we are using the fictitious material concept and not the equivalent material concept. This is what I was mentioning before. Cracks and notches are different. Notches do not have a zero, let's say zero radius on the tip, and then the stress fields are different, and we should develop specific methodologies addressing this particular situation. Because if not, if we treat notches as cracks, this would be a really conservative practice. Well, then, as I said before, the material being analyzed is short glass fiber reinforced PA6, with the fiber content being fixed at 10% weight percentage. We are introducing in the material different notch radii from 0 millimeters up to 2 millimeters. So the first situation will be a crack-like defect. And then we will consider two different amounts of moisture, 2% and 5%. This latter value corresponds to the saturation value. That is, the material is not capable to absorb more moisture. We have the material in pellets, and by injection molding, we fabricated a number of specimens like the one on the top in the figure, tensile specimens. Some of them, just a few, were used to tensile testing, and the rest of them were cut in the middle part to obtain the fracture specimens as that shown in the lower part of the figure. The defects were performed by machining the material, and except for the crack-like defect, which was obtained by sewing. And this is the fictitious material concept is based on a modification of both the tensile and the fracture curves. In the case of the tensile curve, here you have on the left side, you will have the tensile curve of the real material, which is clearly non-linear, and we have to substitute this curve, this behavior, by the behavior on the right side, on which the area, the shadow area, is exactly the same in the two figures. The ductility is fixed, also the same. So on the right side, we just have to change the slope till the the area equates the area on the left side curve. So by doing so, we obtain the tensile parameters in terms of Young modulus and ultimate tensile strength of the fictitious material. This latter value is given by is straightforward, that it is given by the formulation shown below. Something very similar is required for the fractal behavior. We have on the left side, we have the real behavior of the material in terms of load displacement curve, and we have to substitute this behavior by the one on the right side, on which the displacement at failure is fixed at delta U, and we have to change the slope till the areas are exactly the same. In this second curve, we obtain the theoretical failure load, this PF star, for the fictitious material. And by introducing this PF star into the formulation shown below, typical formulation in linear elastic fractal mechanics, we will obtain the fractal toughness of the fictitious material. So with these two modifications, we obtain the ultimate tensile strength and the fracture toughness of the fictitious material. This, we may apply the average stress energy density criterion. Here, just remember that we have to compare the average strain energy introduced in a control volume on the defect tip with the material capacity to store this average stress strain energy density. The control volume is given by this R shown on the upper part of the slide, which depends on the fracture toughness and the ultimate tensile strength of the fictitious material, and the material capacity to storage the strain energy density is given by the second formulation. From this we compare this value with the average stress energy density introduced in the material given by the formulation provided by Lazarin and Berto, shown on the paper. And here you have the results. Concerning the tensile curve, you may see here a clear effect of the moisture. If we increase the moisture on the material, the ductility increases, but the tensile properties are reduced quite a lot. We have to apply the fictitious material methodology to these curves and also to these other type of curves, which are the fractal curves. Here you have the curves obtained in cracked specimens with 2% on the upper side and 5% on the lower side of moisture content. And you see here a clear effect of the moisture content as well. Here, what we show here is on the first table, we see the experimental results in terms of load-bearing capacity of the different specimens and the different areas below the curves. And on the lower table, you see the different fictitious material properties that has been obtained from the reasoning explained in some slides ago. So with all these, we just have to compare the average strain energy density introduced on the defect tip, again, as I said before, provided by Lazarin and Berto formulation, with the capacity of the material to store this strain energy density, which is given by the last column on the table below. So we obtain the predictions of the fictitious material concept and average strain energy density combined criterion, which are given on the second column from the right, which may be directly compared with the experimental values. Showing the last column the discrepancies. For the 2% moisture content, the predictions are really good, and for the 5% moisture content, the predictions are reasonable, but not so good in a couple of cases. I mean, these values are reasonable when we are talking about fracture, but the discrepancy of a discrepancy of 30% is not so good result. In any case, the average discrepancy is around 12-13%, which is quite a quite decent result. So, as a conclusion, this paper has presented the application of the average strain energy density criterion to highly nonlinear materials, which requires, of course, the application of elastic plastic correction, which is given here by the fictitious material concept. The resulting combined criterion has been applied to short glass fiber pH6 with 10% weight of fiber and two different levels of moisture content. And the results obtained demonstrate that this criterion is able to predict reasonable estimations of the experimental loads. And it is then a useful tool in the fractal analysis of non-linear materials, using linear, elastic, and of course, much more simple tools. So I'm open to any questions from the audience. Thank you very much.